In this screencast, we'll look at some basic ideas in probability theory. We're going to start simply with an example that will help us see some of the key features of trying to analyze the probability of an event occurring. So here's the scenario. You flip 3 coins. What's the likelihood exactly 2 of them are tails? So first, the word likelihood is a synonym for probability. So what's the chance? What's the likelihood? What's the probability of getting exactly 2 tails? You see this kind of stuff all the time. When you look at your weather app on your phone and it says 60% chance of rain, that's a probability. So let's go through and explore this. You're flipping 3 coins. That's the probability experiment. And we want to find out what's the likelihood exactly 2 of them are tails. Let's just get a sense of what could possibly happen first. It's very possible that you could flip 1 coin, get a tails, the next one, get a heads, and the third one, get a tails. You could also get something like a heads, and then a tails. Or you could get perhaps a tails, and then a tails. So what we need to understand to be able to figure out what the likelihood of getting exactly 2 tails when you flip 3 coins is the idea of sample space. The sample space of an probability experiment is the set of all possible outcomes. So what we've started to generate here, and this bracket is what people use to denote a set, we've started to generate the sample space. Let's just call it S. So we'll use S to represent sample space. So we've started to generate the sample space here for this experiment. And if we were able to figure out all the possibilities, we could then go through all the possibilities in the sample space and see which one of them have exactly 2 tails. So for example, this one has exactly 2 tails. This one does not have exactly 2 tails. This one does not have exactly 2 tails. And basically our probability would be the number of outcomes that have exactly 2 tails divided by the total number of outcomes. So we need to be able to get this entire sample space. The way we're doing it right now is not very organized, and there's a decent chance we're going to either miss something or we're going to repeat something. So what we're going to do is create what is called a tree diagram. Tree diagram is a graphic that shows the entire sample space of a probability experiment, and it's something you should be able to do. So let's go about doing that now. Often people like to put just a start block here. You don't have to if you don't want to. And ultimately, a tree diagram pays attention to what happened on each of the 3 flips and what happened on the previous flips. So you'll see what I mean in a moment. So flip 1. After flip 1 will come flip 2. And then finally, you'll have flip 3. What can happen when you flip the first coin? Well, the only possible outcomes are heads and tails. And there's a reason I'm spreading these out. You'll see in a while. So from the start, you flip the first coin, you can get either heads or tails. Now on the second flip, we're not simply going to just say it could be heads or tails, which is true. We want to see what you could get on this based off of what happened on the previous flip. So for example, right here, the first flip was the heads. But then when you flip for flip 2, you could get a heads or a tails after having got a heads first. And over here, in flip 1, we got a tails. But after getting a tails, in flip 2, you could then get a heads or tails. And we continue down to flip 3. Well, from flip 1 to flip 2, you could have gotten a heads and then a heads. And then once you've gotten a heads and a heads, then flip 3, you could get a heads or a tails. And in this route, you got a heads and then a tails in flip 2. You could still then get a heads or a tails in flip 3. The previous flips don't affect what happens on the latter flips. They're independent of one another. So over here, we got a tails on the first flip, a heads on the second flip. Now we could then get a heads or a tails on the third flip. And in this final route, we got a tails, and then for the third flip, you could get a heads or a tails. This is the entire tree diagram, and this tree diagram shows you all the possible outcomes in the sample space. It also shows you how many there are. We'll look at that in a moment. So let's actually write out the sample space now that we have an ordered diagram to help us figure out exactly what the outcomes are without missing any of them or repeating any of them. So this first path, we want to go through all the paths from start to the bottom. So you got heads, heads, heads is a possibility. The next path you've got from start is heads, heads, tails. I'm going through this systematically to make sure I don't repeat or miss anything. The next path through the tree is heads, heads, tails, heads. The next possible path here is heads, tails, tails. Then you've also got tails, heads, heads. You've got tails, heads, tails. You've got tails, tails, heads. And finally, the last one here is tails, tails, tails. There's no order to these, but this is a systematic way of making sure we capture all the possible outcomes and we also don't repeat any. So if you go through, you see we've got 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. And how many of them are what we want? And again, our experiment, we want to find out the probability of getting exactly 2 tails. So let's go through and circle the ones that have exactly 2 tails. This one does not. This one does not have exactly 2 tails. This one does not. This one does. It's got heads, tails, tails, has exactly 2 tails. This one does not have exactly 2 tails. This one does. This one also does, tails, tails, heads. And this one does not. So the likelihood of getting exactly 2 tails when you flip a coin 3 times, or flip 3 coins, those are equivalent ideas. There's 3 scenarios that give you exactly 2 tails. 3 out of 1, 2, 3, 4, 5, 6, 7, 8. So the probability here is there's a 3 in 8 chance, or 3/8 chance of getting exactly 2 tails when you flip a coin 3 times. Before we look at another probability experiment, let's look at some major important features of probability. First, with the previous problem, what was the likelihood of getting exactly 2 tails when you flip a coin 3 times? We got the probability 3/8. That 3 was the number of desired outcomes. There were 3 of the 8 outcomes that had exactly 2 tails in them, not more, not less. And the 8 was the total number of outcomes. In general, that's how theoretical probability is defined. It's the number of desired outcomes divided by the total number of outcomes. Since theoretical probability is the number of desired outcomes divided by the number of total outcomes, it follows immediately that probabilities are always between 0 and 1. For example, if you have the number 8 as your total number of outcomes, what's the highest number of desired outcomes amongst all of them? Well, 8. You could never go higher than 8 desired outcomes because the desired outcomes are in the set of total outcomes. And 8 out of 8 is 1, or 100%. So that's the highest percent, or 1 is the highest number you can get for a probability. For example, 200% makes sense in business. You could have a 200% profit, but 200% does not make any sense in probability theory. Also, what's the least number of desired outcomes you could have out of, say, 8? So for example, what's the likelihood of getting exactly 4 heads when you flip a coin 3 times? Well, none of them are your desired outcome because you can't get 4 of anything. You're only flipping it 3 times. So 0 out of 8 is the least probability we could possibly get. 0 divided by 8 is the number 0, or 0%. Notice that probabilities can be represented by fractions, numbers, or percentages. It doesn't matter. You can write them in any of these forms. Also, another important thing that is valuable in probability theory is the idea of how complementary events affect each other. So for example, in the previous problem, we saw that there was a 3/8 chance of there being exactly 2 tails when you flip a coin 3 times. What if I were to ask you, what's the likelihood that there would not be exactly 2 tails when you flip a coin 3 times? Well, that's all the other possibilities. If 3 of the 8 outcomes were desired, then the other 5 are the non-desired ones. So there's a 3/8 chance of getting exactly 2 tails when you flip a coin 3 times. And there's a 5/8 chance of not getting exactly 2 tails when you flip a coin 3 times. In general, the probability something won't happen is 1 minus the probability it will happen. So let's look at another example of that. If there's a 60% chance of rain today, then what's the chance it will not rain? Well, you take the whole, which is 100%, minus the 60% chance that it will rain. That'll give you your 40% chance that it will not rain. In general, these are complementary events, and their probabilities need to add up to 100% or up to 1.